are. All right, thank you, Dr. Guice.
Okay, well, yeah, thanks very much for the introduction, Bronwyn. Thanks for the invite. It is, yeah, pleasure to be here. Let's move this out of the way. Yeah, the poll results are interesting. Maybe I'll convince some people over the course of the next, I don't know, 45 minutes or so that maybe the igneous and metamorphic are slightly more worth our while. We'll see how I do on in this talk. So yeah, as I say, I'll talk a little bit about some of the geology of Maryland, specifically some rocks that look a little bit like this, sort of northwest of downtown Baltimore, extending sort of from the suburbs out to the outskirts of the city to the west. Collectively, we refer to these groups of rocks I'm going to talk about today as the Baltimore Mafic complex. Now, I will explain a little bit about what that means as we go through. Before I do that, I think it's important to sort of acknowledge that I'm going to present some stuff towards the end. It's not just of our research, it's not just my work, okay? This is a collaborative effort. Scientists both at the museum where I'm based, at Johns Hopkins, at Carnegie, and at Towson, okay? So this is a real collaborative science project, and the stuff that I talk about, particularly towards the end, is a real collaboration between many excellent scientists at many excellent institutions. Is it going to let me move on? That's the question. There we go. Okay, so what I'm going to try and do here is explain to you why these rocks that we see in Maryland, you can see me inspecting them out just west of Baltimore, why they are important for the formation of the Appalachian Mountains, both the formation of the mountains themselves, the geology within the mountains, and sort of the geology that is adjacent to those mountains. And in order to do that, I'm going to ask essentially a series of questions. So we'll start by asking, why do the Appalachians exist at all? Why then is Baltimore's geology interesting in that context? And then I'll probably spend quite a lot of time on these questions. There might be some terminology that people are unfamiliar with. There might be some kind of schematic ideas that people are unfamiliar with. I would encourage, as Bronwyn said, I would encourage you to type some questions into the chat window, and I'll probably try and stop at strategic points, and then we can kind of delve into the questions. Let me get the chat window up here so I can just see them coming in. Might be useful. All right, seems good. Okay, and then once we've kind of tackled these two big questions, I'll probably spend a little bit less time on these final three questions. Firstly, I'll talk about some research that myself and my colleagues have done. We'll talk about what key evidence we found to kind of inform some of our interpretations, and then I'll ask that big question, why should we care about all this kind of stuff? I'm having some problem with my slide flicker, but that's okay. Okay, so question one, why do the Appalachians exist at all? So let's start by looking at a beautiful satellite image of sort of eastern North America here, and we can pick out really nicely the Appalachians starting down here in Alabama, kind of winding their way up through the Carolinas and Virginia and Maryland and New York, up into Canada, and extending all the way kind of north of where this map shows into Newfoundland. So we can see them absolutely beautifully just on this satellite image. And what the Appalachians represent is the collision between two ancient continents. So everything, or most of North America, was once part of a big continent called Laurentia. And the east coast of the United States, including Florida, was part of a completely different continent called Gondwana. And that was separated once upon a time by a really large ocean. So these ancient continents were once separate continents. separated by a huge ocean known as the Iapetus Ocean. And we're just going to hop over for the only time in the talk to Europe to sort of make the point that if you actually want to complete the Appalachian Trail in its entirety, you actually need to go through Ireland, you need to go through the United Kingdom, and you need to go all the way up through all those beautiful fjords in Norway. It is the same structure that we see in Norway, UK, and Ireland is the same structure that we see in the Appalachians in North America, all part of, once upon a time, part of the same system. And just to focus on my place that I grew up, the UK, for one moment, you will notice the border, the boundary here. That is pretty much exactly the boundary between England and Scotland. And I think many of my Scottish friends are quite pleased to learn that their origin is one sort of a separate continent to that of me, and may explain some of the, particularly the soccer-based animosity between Scotland and England. Okay, so let's hop back over then to North America. We've got those two ancient continents, Laurentia and Gondwana, as I said, once separated by this huge ocean. So you might be thinking to yourself, well, when was this ocean, when was it there and where did it go? And in order to kind of answer that question, we need to turn the clock back, not to last week or last year or last decade, but 500 million years ago. So this is long before the dinosaurs were extinct. It is long before dinosaurs even first appeared on Earth. It is 500 million years ago, at a time when these little guys, trilobites, I see there was some fossil-based chat in the chat window. I suspect you'll be familiar with these guys, but these guys were roaming around on the floor of the Iapetus Ocean at the time that we're talking about here, 500 million years ago, pretty long time ago. And you might also be wondering, well, where did the oceans go? So I'm going to do a bit of use this schematic diagram here just to try and explain where oceans go when we lose them. So this is a cross section, so it's kind of a block diagram. This is the cross section, so you've got to imagine we've taken a slice through the Earth, and then this is the surface. This is the land surface on the top here. So we've got one continent over here. We'll have another continent over here off the diagram, and then here's our ocean between the two. Now, an absolutely critical thing that we need to kind of understand, if we're going to understand how we close these oceans, is the rocks and the minerals that make up the crust that sits underneath our oceans is fundamentally different to the crust that sits underneath our continents and makes up our continents. So the oceans are made up of relatively dense minerals and dense rocks, whereas the continents are made up of relatively light minerals and relatively light rocks. Now, we get both mineral types and both rock types in each other. So some of the same minerals that we get here, we also get here. But as an average, there is way more light material in the continents and way more heavy material in the oceans. So what that means is that when those two continents move towards one another via continental drift and plate tectonics, the heavy one wants to head down. The heavy one wants to head back down into the bowels of the Earth, and the continents are happy sitting above the surface, forming these nice land masses that we can live our lives on. And this is what happens in this instance. It happened 500 or 450 million years ago in the Appalachians. So we got our other continent over here by my cursor, and as this ocean is subducted, we say, subducted beneath the continent, our other continent inches its way towards the other continent until a time when no ocean is left at all. And something I just want to point out while we're on this little cartoon is these kind of black blobs. in here. Okay, so typically what happens when one of these continents, or the oceanic crust, goes underneath one of these continents, the oceanic crust has quite a lot of water bound up within it, within the minerals within it. And when this plate goes down, it releases that water. It releases the water into the overlying rocks. And what that does is it facilitates melting. So we start to create some magmas above this bit of crust that has gone down. And those magmas eventually can rise up and form volcanoes. So if you think about just in the Andes, for example, in Chile, there are a whole series of volcanoes that exist along there, and it is this process that is causing those volcanoes to exist. It's just a little aside there, but maybe useful later in the talk, who knows. Okay, so we've got rid of our ocean, or subducted our ocean beneath the continent. What now? Well, now we've got two things crashing into each other that neither of them want to go down. Neither of them are interested in heading back down into the bowels of the earth. And so they crash into one another, and essentially the rock buckles and we get the formation of mountains. So one example, modern day example of where that's actively happening is the Himalayas. So we got India down here, China up here. These two plates, again, much like the Appalachians, once there was a big old ocean between these two, and now they're crashing into one another, and there is a big mountain range there. So perhaps once upon a time, the Appalachian Mountains looked a little bit like this. These beautiful angular mountains. We've got a glacier down here, some glacial lake, and yeah, really quite stunning environment. And over the last 300 million years or so, what has happened is erosion has happened. And we've gone from these high mountains, angular surfaces, and we have created the kind of rolling mountains that we see. I believe this image is from the Blue Ridge. So I think if you're interested in hiking rather than climbing, you should be pretty grateful of erosion because it's made your life just a little bit easier than this kind of environment. I would suggest at this stage, if anyone's got any questions and they want to put them in the chat window, feel free. I'm just going to sum up kind of what I've just said on this slide. So feel free to put them in there, and hopefully I've not lost anyone. If I have, please do say. I'm happy to go over stuff. So just to summarize that then, here are our beautiful Appalachians here in the eastern North America. And what they represent is kind of two key processes. First, the subduction of this oceanic crust beneath the continent, and then secondly, the collision of those two continents to form the mountains themselves. And when we look at the Appalachians, when we look at the geology of the Appalachians, that is what is recorded. It's this process and it's this process. So that is why they are there. That is why the geology is there, both within the mountains and broader. So as long as that's, are the plates that created the Appalachians still moving towards each other? No, we've really fast forwarded since the time of the Appalachians. So I mentioned that the Appalachians continue into Europe, and that is because these continents once sat next to each other and they were all part of the same thing. So you had a lot of Europe and North America essentially docking to Scotland and the rest of North America. And then what happened is the Atlantic opened. So we've changed regime and the Atlantic has started to open, and now we are moving, you know, I am moving slightly further away from my family every day because these new crust is being created in the middle of the ocean. So I would encourage you, Google Earth is just wonderful for seeing all these processes. And I would encourage you, if you're not already aware, to go to Google Earth and just look at the middle of the Atlantic Ocean, and you can see much lighter blue colors, and that's because it's much shallower there, where you've got this string of underwater volcanoes, which represents these two plates moving apart. And yes, Gondwana was indeed the continent where South America and Australia, Antarctica, yeah, absolutely, all part of that same continent. So all of these land masses, as you can see, they really move around Earth, and they, when you're looking on the time scales of millions of years, you can see Australia is quite a long way from Florida, but they were once part of the same land mass. Okay, I'll give a couple of seconds to see if anyone else wants to add a question. Okay, let's move on then. So hopefully you're all with me. That's question 1 out the way. Question 2, why then is Baltimore's geology interesting in this particular context? Well, we'll start by looking at a geologic map, okay? So just to try and orientate yourself, downtown Baltimore's down here at the cursor. Here's the Patapsco River. And there's a few highways in here just to orientate yourself. So hopefully you've kind of got your bearings here. And all of this gray stuff to the right of my cursor, these are pretty young rocks. So you sedimentary aficionados should certainly head down here. There's lots of gravel and sandstones and siltstones, some really young stuff and some slightly older stuff as well, on the order of 150 million years or so. Yeah, in my world, that is pretty young. Appreciate it is also quite old. What we're interested in terms of the formation of the Appalachians is kind of all of the reds and the browns and the greens. So all of these rocks are associated in some way with the formation of the Appalachian Mountains. And specifically what I'm going to talk to you about is these pale green colors. Okay, you see my cursor extending from, this is quite close to Johns Hopkins University, actually, the Earth and Planetary Science Department, and extends kind of all the way out of the city. And you're kind of very much in a rural area by the time you get out here. So it extends through the suburbs. And then there's a couple of other areas at Soldier's Delight. Many of you might be familiar with Soldier's Delight, and Bear Hills is a kind of lesser known, smaller locality as well. So it's these pale green rocks that we're interested in. And these are Ultramafic rocks. So a group of rocks that we call ultramafic. So what is an ultramafic rock? Well, fundamentally, they start life as igneous rocks. Okay, so as you all know, we can create an igneous rock traditionally either by formation from a lava flow, where magma is headed up to the surface and cooled really quickly to form a rock, or alternatively, beneath those volcanoes, we have magma chambers that sit beneath the surface, and they might cool really slowly. Obviously, it's a bit hotter down there. It takes a lot longer to cool down a rock, but it might be thousands of years. We cool down our rock, and we might be able to form these ultramafic rocks in the magma chamber too. So that's like just two examples of how we can make our ultramafic rocks, or our igneous rocks more broadly. And the minerals that make up this group of rocks called ultramafic are olivine and pyroxene. Now, some of you may have encountered these kind of minerals. They're reasonably common. These are, I should say, really gem quality minerals. These are not what I normally find in the field, so don't think that this is representative. And our ultramafic rocks just represent a combination of these two minerals in varying proportions. So sometimes we have lots of olivine, Sometimes we have lots of pyroxene, and we can actually see this is a field photo from the northwest Highlands of Scotland. Somewhat paradoxically, these brown layers, brown weathered surface, have loads of olivine in them, and these really grey layers have loads of pyroxene in them. And what you can see from this image is that there's kind of a gradation between these two end members. So if you look from here, it's very grey, and then we get increasingly brown in this direction until we have a very, very brown rock. And that would be a lot of olivine. Here, a lot of pyroxene, and kind of a combination of the two in these intermediary layers. So let's talk about rock names then. So we're still in this realm of ultramafic. And if we have more olivine than pyroxene, we would call that mineral, that rock, I should say, peridotite. If we have more pyroxene than we have olivine, we would call that mineral pyroxenite, somewhat originally being full of pyroxene. So these are our two end members, and these are both classified as ultramafic rocks, despite the fact that they look quite different. So just to kind of reinforce what I said on the last slide a little close up, here's our really pyroxene rich layer. So this is a pyroxenite. Here, over here is our peridotite, and you can see the kind of gradation between the two occurring in this layer. A classic rock hammer for scale, why not? So that is how ultramafic rocks look when they're nice and fresh off the production line. They've just crystallized from a magma or a lava. But, and there is always a but, they really do not like fluids, and Earth's crust beneath our feet is full of cracks. It's full of cracks that fluids can travel through, and fluids do travel through, and particularly when you're looking at rocks that are really old, hundreds of millions of years, they've often interacted with these fluids. And when they do, the rocks change massively. Okay, so we can take a slice of our rock and look at it under a microscope. We can put it on here, shine some light from beneath, and that light will head through our sample, and we'll be able to have a look at its kind of characteristics under this light. So the colors that you'll see are not representative. We play around with the settings effectively, but this is what it would look like fresh off the production line, or something close to this at least. So we have, here's our mineral olivine. You can see it's really cracked, and that's really distinctly of olivine, so distinct for olivine. And all of these different colors with the cracked texture are olivine. So this orange, pink, the blue, the purple, all of these are olivines. And here is our pyroxene. So it's this brown mineral, and you'll notice that the key difference when we're looking at this under a microscope is these parallel lines. They all go in the same direction. And what this represents is a feature that we call cleavage. You might be familiar with that word if you've encountered biotite mica, for example, causes biotite to split into those beautiful planes that we see. So this is like kind of the before shot. However, those nasty fluids can come along and alter our minerals, and they alter them to a mineral called serpentine. And all of these these are all tiny little mineral grains. And so we start with this and we end with this. And that makes my life as a research geologist interested in these rocks quite a lot more difficult, to be honest. But it's part of the fun. So this started life as a peridotite, as I said, and it ends life as a serpentinite. Now, the crucial thing to say here is that these are still ultramafic rocks. I used that word earlier. We're interested in ultramafic rocks. They're still ultramafic. They will continue to be ultramafic unless something very drastic happens. But it is the minerals that have changed to kind of get used to the new conditions because of these fluid interactions. So there's been a lot of terminology there, I appreciate. So I hope that I haven't lost too many of you. A lot of rock names, a lot of mineral names. Hopefully you're familiar with some of them already. I suspect all of you have seen a lot of these kind of things. So if anyone wants to pop any questions in on that section, before I move on to the real part of why Baltimore is interesting, feel free to go ahead. I can wait for a couple of minutes. Looks like we're good, I think.
I think so.
Okay. All right, good to hear that you're still with me. Okay, so let's bring it back then to these Ultramafic rocks in Baltimore. There's a couple of images here. You can see a little golf cart in the background, which gives away one of the sampling locations. You can also see my colleagues, Daniel Viette, Naomi Becker, and Freya George, all at Johns Hopkins, here as well, taking some notes. So these rocks, where did they come from? Now, there's two quite logical hypotheses that these rocks could represent, but the hypotheses have really different implications for the kind of origin of the rocks that sit underneath Baltimore. So hypothesis one is that these rocks represent a kind of fossil magma chamber. Glad I used that fossil word with all the fossil folks in today. The other hypothesis is that these are fossilized ocean crust. That crust, remember that I said, that sits underneath the oceans and that is really distinctive. Those are the two options. Let's just go into that a little bit more. Here's hypothesis one. Perhaps these rocks formed underneath a volcano in a magma chamber that looks something like this. Alternatively, what we could be looking at is a section of oceanic crust. And the reason this is possible is because this is a section. This is a classic section through oceanic crust and down into the mantle. So just a little bit of terminology here. This word lithosphere, essentially what it means is we're including both the oceanic crust itself, so the crust that sits underneath the oceans, and the topmost layers of the mantle that sits underneath. Okay, so we've got a little bit of mantle and we've got all of this crust. I'll probably just use ocean crust for shorthand. We don't need to get into the weeds on terminology here. But what is important to note is that the bottommost section of ocean crust is made up of these rock types that I talked about earlier. Okay, so this is one logical hypothesis. So this lowermost section, the mantle peridotite, is, as the name suggests, dominantly made up of peridotites. And when we get into this lowermost crust, these layered ultramafics, we kind of have both of these kind of rock types in alternating layers. And to bring us again back to that cartoon that we looked at the start, you can see just how far away these possible origins are. One, our hypothesis one, let's start over here, would mean we have these magmas coming up from that plate that's been subducted and forming in the continental crust here. Alternatively, we've had a slither or kind of chunk of this ocean crust that normally goes down, but has found itself whacked onto the land for some reason or another. So two really different hypotheses and important for what sits underneath Baltimore today. Okay, again, I'll give you an opportunity at this stage just to pop in any questions. Feel free to do that. If not, we can spend just a few seconds, I guess, looking at either me examining the rocks or the beautiful Appalachians. I think I know which one I would prefer.
I have a question, George. Are there other places? I mean, is Baltimore unique for these particular formations, or are they found other places? in North America.
You mean the rock types themselves?
The ultramafics and the.
Yeah, they're not particularly common rocks, but they're not. It's not unusual to find them. So yeah, you're not. These things, we get little slithers of these kind of rocks throughout the Appalachians. So there's some in Canada. There's quite a few in Newfoundland that you can go and look at. There are actually some just south of DC. There are some Pennsylvania. So they're not a super common rock type like sandstone or a basalt, but they're, we know they exist, and they can exist in these multiple different ways, which is why we get them. But not super uncommon. Okay, cool. Thanks for that, Bronwyn. Okay, let's move on then to our third question, which is what research did we do? We had a lot of terminology and schematic diagrams in the first part of this talk. So let's.
Got one question, George, that just popped up.
Oh, right.
Serpentine found in Scotland.
Yes, serpentine is found in serpentine is found in Scotland. Again, it's not super common, but I have looked at some rocks in Scotland that you would classify as as serpentine. I should say actually about serpentine while we're on the subject. Asbestos is a kind of serpentine. I don't know whether that is new knowledge, but so asbestos, that pesky asbestos, is a kind of serpentine group mineral, and you do occasionally see really long, elongate asbestos grains in the field. I've only seen it in a few places, but it is possible to see. Is it there by the same process as here? Well, the process of changing an ultramafic rock, so like a peridotite, to a serpentinite, is similar everywhere. It's always fluids. Those fluids might have different origins in different places, but it fundamentally is fluids. In terms of the origin of the rocks themselves, no. The rocks that are serpentinites that I've worked on in Scotland and those in Baltimore are, in my opinion, different, and they formed by different processes. So the rock types are the same, but the processes by which they got there originally, those primary igneous rocks, are different. Cool, thanks for the questions. All right, so let's talk a little bit about some of the research that we've done. And we need to rewind to a time when we didn't know what the word COVID meant, where Corona was simply a beer made in Mexico. And back to, it was in August 2019. So I'd only been living in DC, I think, for 2 months at that stage. And I'd become aware that there was some interesting rocks in and around the Baltimore area that might be worth studying. And I'd also learned that there was a group at Johns Hopkins interested in these same rocks. So I reached out, sent them an email, principally this guy here, Daniel Viette, who's a professor at Johns Hopkins. And I got a train over to Penn Station and met this gaggle of geologists in a minibus out the front of the station, right in here. And we kind of went off in search of prospective sites to learn about the geology of this area. Now, as I will talk a little bit more about in a moment, clearly it can be a bit of a challenge doing geology in Baltimore because there is quite a large city built on top, which does restrict your access to the underlying geology somewhat. So we kind of went around looking for locations to sample and locations that we could do future research projects, kind of assess the rocks in these areas to understand the geology underneath. And we were reasonably successful. We found some good sites to go and look at, including some that I'll note in a moment. And we were feeling pretty pleased with ourselves. You know, I'd made some new colleagues and friends, and we've got a research project off the ground, and then we decided to head, of course, to Camden Yards for an Orioles game. I believe the Orioles lost, but I enjoyed the day. I enjoyed the game all the same. Some hot dogs and some beers, and it was a very pleasant evening in the searing hot East Coast sun. So that's how things started. And over the next couple of weeks, couple of months, we set a couple of dates to just go out and look at the rocks and try and assess them and grab a couple of samples. So you can see all of these black crosses on the map here are places that we have collected samples from. So you'll see, for example, we collected 8 samples from Hollerfield Quarry. It's kind of an overgrown quarry just outside of the city. But 2 locations I want to highlight here, which I think illustrate the points that I was making about this urban geology situation, are this Forest Park Golf Course and Ashburton Reservoir. So this is a little old, this satellite image, because for the last few years, there has actually been some construction and excavation work going on, because they are making what they call the Ashburton Tanks project. Essentially, they want to cover over this water source and have an underground water storage facility. And in order to do that, they've had to excavate out this reservoir. And that was a brilliant opportunity for us as geologists. I'm very lucky that we happened to stumble across it as they were doing this work, because they had to dig out a lot of rocks that were not normally at the surface. So we went and spoke to the guys that were doing it there, and they kindly allowed us to go in and kind of rummage through their rubble and grab some samples. So it was a really great opportunity for us, and very lucky, like I say, that we caught them at the right time. If we went back now, they've nearly finished the project, we wouldn't be able to see any of the underlying geology. So that's really a good moment. As you can see, there's not going to be many rocks in this area. It's very much a kind of suburban city area. And yeah, the other area that I want to highlight is this golf course. So again, kind of suburban neighborhood we've got going on here with this golf course in the middle. And we're very fortunate that there are 1 or 2 exposures of the rock underneath on this golf course. So again, we went and spoke to the people who run the golf course and kind of asked timidly if we can go and look at their rocks, if they don't mind, and they were perfectly happy with that. So we went and checked out their rocks, and obviously trying to get a little sample, and some guys come along the fairway and play onto the green. We stop hammering while they take their putts, a bit of polite applause as they do so, and then we get on with the task at hand. So there were some interesting sample locations, and I think it just really shows that geology is everywhere, right? We assume that geology has to be in these remote locations in the middle of nowhere that are really inaccessible to most people, and actually they're just in and around the city, and we can go and look at these things in the city as well, which is just, I think, really cool, and yeah, hopefully really good to get people involved who ordinarily wouldn't be involved in these kind of things. So I just saw something in the chat about Rasberg amphibolite. I've not actually ever been over to the Rasberg amphibolite area. I don't know whether any of my colleagues have. They might have. So yeah, we didn't sample this. These are kind of a different rock type, and so we were targeting these lighter green units. And yeah, the Bear Hills location is I think it's called Copper Mine, and I think there's some sort of like a family park or something there. I think there's in the entrance to that park there's a bunch of kind of an old quarry, situation there, which we could go and take a look at. So that was ideal, but only a couple of samples from there. As you can see, it's a very small little body. Okay. All right, so we've got our samples. The question now is kind of what do you do with a sample? You got some rock, that's all very well and good, but how do you go from that rock to then having something that, as you said at the start, Bronwyn, got picked up by National Geographic and Washington Post and all these media outlets? We were certainly not expecting that when we started the project, that's for sure. So how do you go through that process? Well, there's two tracks to this. Okay, so we're going to treat our sample in two different ways. So track one, what we're going to do is we're going to take a diamond bladed saw and we're going to cut our rock. And we're going to cut it relatively thin, maybe no more than, I don't know, 1/3 of an inch thick. We're then going to attach that to a glass slide with some special glue. And then we're going to grind down that sample and polish it so that it is transparent. So it's essentially see-through, and we can then put it into the microscope. And when light passes through the minerals, we can take a look at them, and they interact with that light in different ways, depending on the different minerals. So as you saw, olivine looks a certain way, orthopyroxene looks a certain way, or pyroxene broadly looks a certain way. So that's one thing we're doing. And what we can also do with these thin sections is we can put them in a fancy piece of kit in the Natural History Museum. I've spent quite a bit of time in there over the last couple of years. And essentially what we do is we fire a beam of electrons at our rock. That beam of electrons then interacts with the minerals, and depending on the elements that make up those minerals, certain signals come back. Okay, so if you've got a lot of silicon in your sample, you'll be able to measure that. A lot of calcium, a lot of magnesium, whatever is made up in your rock, you'll be able to measure that. And so you can hit one point, you can hit another point, you can compare the chemistry of those different points, and you can really get a feel for the chemical makeup of your rock samples. So that is track one. We call this kind of in situ work, because we're taking the rock as it was found, and we're able to kind of navigate and look at the minerals and their relationships. You know, why does one mineral occur here and one mineral occur here, etc. Track two, we take our same rock sample and we crush it up to a gravel, and then we completely pulverize it to a fine powder. And you can see the powder kind of residue just a little bit, and most of the powder is still in here. This is a ring mill, something we use to crush up our samples. And essentially what we're doing there is we're homogenizing the sample. We're averaging the chemistry of all of our minerals, and we're going to see what that the chemistry of the whole rock together is. So we can prepare those powders into a kind of glass, and then we can put it on a different piece of fancy equipment at Johns Hopkins University. This is called you do not need to remember this, a laser ablation inductively coupled plasma mass spectrometer. Okay, we just call it the laser. We don't need to go into all those terms. And essentially what we can do with this is we can measure the elements again that make up our rock powder, but crucially we can measure elements that are really, really low in abundance, so that are only in the rock in parts per million abundance, so really low. We call these trace elements, and I'll get onto in a moment the reason why we might want to do that. So these two tracks are how we're assessing our rocks. I've lost my cursor, there we go. Okay, so this is the first 3 questions done and dusted. I'm just going to kind of do these 2 final ones together. So if you've got any burning questions at this stage, feel free to chime in. Not seeing anything come in the chat, so I think we can probably crack on. All right. So, okay, so we had a bit of rest during that section, but we're going to get back into the weeds now. So, what interesting evidence did we find? Well, let's start with that second track. So, those rock powders. What did we learn from the rock powders? Well, as I said, we learned, we were able to analyze trace elements, so elements that have super low abundance. And the reason we want to do that is because these elements can really tell us about different magmatic environments. So for example, if I were to take a rock from Hawaii and a rock from the Chilean volcanoes, and I were to prepare them in the manner that I've described to you, I would be able to tell that they were formed by very different processes, tectonic processes, just by looking at those trace elements. Okay, so one is formed in this subduction setting, and Hawaii is a hotspot. So they have two different chemistries, and we can tell that by the trace elements. So let's take a look at our rocks from Baltimore. I'm going to talk you through this figure here. So there's a series of trace elements along the bottom. So we've got rubidium and barium, things like that. Perhaps you've heard of, clearly you've heard of uranium and zirconium. And on the y-axis, it's just simply abundance on a logarithmic scale. So for example, 0.01, 0.1, 1, etc., heading on up. And all we've done here is we have taken our sample and we've divided it by a kind of standard value. And we subdivide all of the rocks we analyze by this standard value, just so that they're a bit more comparable. And then we plot them on here. And what you will notice here, actually, I should flick forward a slide. So this dashed line is where most ultramafic rocks that I look at sit on this plot. They sit around about 1 in normal cases, but that is not the case for the rocks that we have sampled here. They are really, really depleted in trace elements. The concentrations of these trace elements are super, super, super low. So just to try and give you an idea of how little of these elements, if you imagine you need to cook a meal in the evening and you need some rice. You weigh out the rice you need, and great, that's what you want for your meal. Someone comes along and takes 90% of that rice. The amount that's left would leave you sitting all the way down here. Now, only one of our samples sits around there. If you then take away another 90% of what's left, it leaves you down around by where these samples are. You've got very little rice left from where you started. So the difference between this is absolutely huge. And the crucial thing to note here is this grey field that I've put on underneath our samples represents rocks that sit at the very, very bottom of that sequence that sits underneath the oceans. So if you go to the very bottom of that sequence that sits under the oceans, they have this same chemical signature that are really, really depleted in these specific elements. So that suggests one of our two hypotheses is correct. If the other hypothesis was correct, perhaps we'd be sitting up by this line. Okay, so that's the kind of second track that I described in our sample preparation. Let's take track 1, so those thin sections that we looked at, and specifically a rare mineral which we call spinel group minerals. So again, this is a group of minerals, and there are different minerals within this. So you might have heard of chromite, you might have heard of magnetite. These are reasonably common minerals, and these are all part of what we call the spinel group. Okay, so they have this big umbrella term. And you can see these are some of the rocks that we studied, and you can just about see these rare spinel group minerals throughout the rock. And the neat thing about these minerals is that when all the other minerals are unhappy and being affected by these fluids and altering to other things, these guys stick around. So they can preserve the story from that original rock that formed from the magma that cannot be recorded by the rest of the minerals, which is really, really cool and crucial to the story here. So let's talk a little bit more about these minerals. So here's a map. So this is a map of the chemistry of this specific mineral grain. this is iron. The hotter colours, there is more iron. The colder colours, there is less iron. The same can be said for aluminum as well. So it's a little bit like, I guess, analogy here that works probably is tree rings, in that we're recording different time and a different process for these outer layers than we are from the inner layer. And what these outer layers is, they represent that fluid story. So that fluid that completely affected all of the surrounding minerals has affected this mineral to a certain extent. But look at this core. This retains the original chemistry of the middle of the mineral, which can help us to understand where these rocks came from. And if we plot these on a diagram with chromium on one axis and aluminum on the other, these spinel group minerals, specifically chromite, sit within the mantle array. Now, if our alternate hypothesis once again was correct, we would expect them to sit within this field here. This cumulates just basically means magma chamber. It's a fancy word to say magma chamber. Okay, so we've now got two pieces of evidence that are suggesting that we're looking at these kind of ocean crust rocks. So, I mean, why does this matter? I think some of you might be thinking, and there's a few answers I could give here, but the first one is just to say there is an ocean crust preserved in Baltimore. That doesn't happen very often. There is a reason we're excited about it, and that is because it does happen, but it doesn't happen very often. And if you think about how difficult it is, if you think about that figure that I showed you earlier, most of this ocean crust heads on down beneath the continent. We never see it again. It's destroyed. And if we want to study the oceans, there's quite a lot of ocean between the rock underneath and the surface. It's quite difficult to get to. And so when we get these rare glimpses where that is whacked onto the land, we are able to understand what the ocean crust is made of, what the mantle underneath that is made of, and understand these processes, these igneous processes that happen to form crust. And these are fundamental drivers of plate tectonics on Earth. So, yeah, just to kind of reinforce that these lighter green rocks represent exactly what I'm talking about. This photo is from Bear Hills, actually, from here. And this photo is from the Holyfield quarry down over here. Okay, so let's just place these rocks then a little bit more in the context of this kind of sequence of rocks that I spoke about earlier. So, as I mentioned right at the start, this bottom two sections represents these ultramafic rocks. We think that these guys and the guys at Soldiers Delight represent this lowermost area, the mantle peridotite, and we think that these more layered rocks at Holyfield Quarry and that extend into Baltimore towards Johns Hopkins University represent this layered ultramafic unit. That's it at the very bottom of the crust, just above the mantle here. And we can kind of extend this hypothesis to these darker green rocks. So these darker green rocks are what we called mafic. Okay, so you can see the relationship with ultramafic. These are just not ultra, and they contain olivine, a little bit of olivine, just like the ultramafic rocks. They contain a little bit of pyroxene, just like the ultramafic rocks, but they also contain a lot of plagioclase. That's the third mineral that we get in these rocks. And these rocks, some kind of preliminary work, some of my colleagues at Johns Hopkins are doing, suggest that indeed we can find these units, which are all mafic rocks, seem to be represented by these darker green colors. So Baltimore probably sits upon most of this kind of ocean crust section somewhere or another. Okay, just to kind of once again bring it back to this figure, we've seen it a few times now, and just to think about how we've got a slither of this ocean crust and we have whacked it up onto the continent. That is now effectively Baltimore. That is what happened. That is the headline story here. Let's just kind of ask again more broadly why this matters, potentially for understanding the Appalachians. So when we come back once again to this satellite image, and I'm going to add on a geology map. So just to orientate yourself, you can see Florida. This is the coast, it's the east coast of the United States, and it's Newfoundland. So Alabama is here, and New York City down here. Baltimore is here. And I want you to ignore everything south of my cursor for now. So ignore that for one moment. There is 3 stars, 1, 2, and only 2 stars, I should say. 2 stars on here. And what these represent is ocean crust that we're very confident is ocean crust before we did this research project. So you kind of asked earlier about where else these kind of rocks exist. And here's an answer. So all of these symbols represent occurrences of these kind of rocks. There are a few more, it should be said, but these kind of represent the main occurrences. And these stars represent a place where we know you have this ocean crust. And so we thought originally, to be honest, that we only got these kind of rocks in the northern part of the Appalachians, and that everything south of New York City didn't have this, and that there must be some kind of fundamental difference in the processes in order for there to be them existing in one place and not in the other. But actually, the fact that we've found this in Baltimore really extends this all the way down, and myself and colleagues are starting to explore several of the examples between Alabama, this Daneville complex that you can see marked here, and Baltimore, just to see whether there are any more of these things along this kind of train of the Appalachians. Okay, so I hope I've not lost you completely. I hope that was relatively clear. And just to try and give you some sort of key takeaways here, let's just recap a little bit. So if we think all the way back to the start of my talk, point 1, the Appalachians fundamentally, they record 2 key things. They record the closure of that ocean called the iapetus that separated those 2 big continents. And it then records the collision of those 2 continents to form the mountains. This was more than 300 million years ago, so before dinosaurs started to walk on Earth. In terms of just defining what an ultramafic rock is, they are originally olivine and pyroxene, and they can then be altered, as we discussed, by fluids to serpentine, and that rock type would be called serpentinite, but still very much an ultramafic rock. And then finally, just what I've been talking about somewhat excitedly is the fact that the ultramafic rocks, and we think the mafic rocks that we haven't discussed too much, in Baltimore represent the mantle and the crust that once sat underneath this ancient ocean, and that what we've seen is a little sliver of this crust, that is this ocean that has mostly been destroyed, and we've preserved it in and around Baltimore. So, like I say, I hope you've been able to follow that. Thank you very much for inviting me. It's a pleasure, and I'll be happy to take any questions and fill in any gaps here. So thank you very much for listening.
Thank you, thank you, thank you. This was wonderful. Can we come back together and as a group so we can share? Wonderful. Do we have any? Oh, yes, I think there's some questions here, or some paragraphs.
Yeah, give me a moment. I'll just I'll read through them.
Yeah. Yeah, I just want to say, I want to echo everybody. This was a wonderful presentation. You did a phenomenal job of taking very complicated concepts and explaining them in a way that we can all wrap our heads around, because it's hard to wrap your head around things that are so you know, that happened so long ago, and it's wonderful. If anybody wants to ask a question and not put it in the chat, you can just use the raise your hand icon, and I can call on you for that too.
Yeah, there's a good question in here about, yeah, Martin's asked a question about how this sequence is all kind of out of order from what you would expect. Great question. We don't know the mechanics of this. That's the simple answer, is to say that we don't know. Most good questions should be responded to with we don't know, because geology is complicated. But what I would say is that this part of the Appalachians has been affected by, kind of simplified the story a little bit, but by multiple collisional events, and with that comes lots of different opportunities for faulting, and it comes with it lots of opportunity for rock to essentially slip past one another. And I think if you look at the geology of the area, these are all little slithers that I suspect have been, you know, faulted up against one another. Did you want to come on in on that, Martin?
Well, I think we probably would agree that this is going to take some multiple working hypotheses for a while to figure out how you spread out this structure the way it's come out. But it's good that you all have shown through the chemistry that it really probably came from deep in the mantle, not just higher up ocean crust, but mantle rocks. And now the question is, how do you scatter them out across all this area the way they are?
Yeah, absolutely. I suspect part of the answer there lies actually in that fluid story that I talked about. When you alter these rocks, they can become quite incompetent relative to other rocks. I wonder about the strength differences between these different, you know, units, whether that makes these rocks particularly susceptible to kind of like chopping up essentially. But yeah, I really don't know. It's interesting, and like you say, the mantle rocks is the crucial find here. Seeing that chemistry, that's when it went from being this is an interesting project to we need to write this now because it's really cool and because it's a significant development for the geology.
Yeah, and Johnny Johnson there and we discussed how this could have been a lot of overturned stuff and a lot of perhaps some naps and so forth going through, getting pushed around in all these collisions.
Yeah, absolutely. And the other thing I'd sort of say on this is I often work on rocks that are way older than this. So these are actually quite young rocks for me. And yeah, it might seem a strange thing to say. I look at rocks that are like billions of years old. And something that is important for us when we look at these rocks is also trying to find these same things, these kind of fragments of oceans. And it's a lot more hotly debated. And part of that debate is a bit like we see in Baltimore. They've been so dismembered and messed up by the tectonism that it becomes almost impossible to relay the full sequence like we would like to see. And so the fact that we're able to use the chemistry and kind of say, hey, we've got this bit and we've got this bit, and therefore we can try and piece it all together. It's super exciting moving forward and looking at really old, even older rocks.
It's almost like you're matching up DNA with the chemistries, the DNA of the rock.
Absolutely, yeah.
Let's see. Daisy wants to know the bare hills. Are they protruding from a fault line, causing them to rise?
Yeah, I suspect that it's an old, that the body there, it's really small. I suspect that the rocks there are bound by pretty old faults, yeah, perhaps 300 million years old or more. And I suspect that it was along those fault lines that meant that it sits within rocks that are different. So you saw it was surrounded by that kind of pale red unit. So yeah, I suspect that it's bound by faults, that little pod of stuff at Bear Hills.
And let's see.
I should also say the problem here is not only the city, but the fact that the vegetation is super thick. You often, the boundaries between these different geologic units on the map, I mean, the map that I showed is very uncertain because, and you know, the Maryland Geologic Survey have done a good job with it. They've done as best they can, but there's a lot of uncertainty in that map. We don't know the nature of the boundaries. We don't know whether they're faults in many cases. We don't know whether they're normal boundaries that you would expect. So it's kind of tricky, and it makes the chemistry or the DNA work, as Bronwyn puts it, you know, even more important in order to try and put this puzzle together as best we can.
Are you studying serpentines out in California?
I'm not. I'm with a couple of colleagues. I'll just admit someone in. I'm with a couple of colleagues actually who were co-authors on this study, Freya and Daniel, and we're looking actually at metamorphic rocks. So we're looking at some beautiful eclogites and blue schists, some high pressure rocks. Yeah, should be. It's pretty cool. We're seeing some spectacular things. So I've come along as kind of basically to learn about some rocks that I don't normally look at and help them out with the field work. So it's been great for me. But there are
when you're looking at the rocks, if they're coming up from the ocean, I guess would there be fossils in them or no?
Probably not in this case. There's a limited amount of sediment, but yeah, I mean, you obviously get fossils from seas, but yeah, you wouldn't expect to see a huge amount of fossils in association with these kind of sequences ordinarily.
Adrian wants to know about the Scotland connection.
Oh, I see. So people are kind of wondering about how it's possible that the Appalachians are still in, you know, they continue into Norway and Scotland. Is that what you mean?
Adrian, is that what you meant?
Yeah. I mean, what is with I don't want the encyclopedia answer, obviously, but because I wouldn't understand it. But the 2-minute version of explain to me this connection between Appalachians and what you're seeing in Scotland. Why what is to you an obvious connection?
Okay, I'm going to try and do that. I've just ripped out a page of my notebook. I'm going to try and use a page of the notebook to explain this. I'm going to have to do a bit of ripping here. See how this goes. This could be a complete disaster. Okay, so let's get rid of my no second. So here are our two continents, and here is Laurentia, and here is Gondwana. And on Laurentia, on my left hand, we have Scotland is like here, and most of North America is like, you know, all of this area. Okay, and Scotland is sat on this continent. And then what happens is they come together, they suture together, and they form this mountain range. And then what happens is the continents reconfigure. Okay, so they've come together, and we then rip this page in a different way. Let me try and do this. So I've now ripped that page in a different way, and then they come away in a different, yeah, that's right. And they come away in a different direction. We open the Atlantic. So then you end up with different bits together that were not together before, if that makes sense. Okay, so we're assembling and then we're taking away in a different direction. And that's what's happened. So the Atlantic Yeah, I saw some thumbs up, so maybe that was not a not a useless explanation.
So what do you see in Scotland that makes you say, oh, that's the Appalachians?
So we see, firstly, I described this magmatic affinity, this magmatic activity when one plate goes underneath the other, and
Right.
then the volcanoes come up. So we see the same age volcanoes in Scotland that we see in the Appalachians. So we see ancient volcanoes like 400 million years old, or 450, 500 million years old in Scotland, and we see them in sort of in the Appalachians, and we see them in Norway. Okay, so that's kind of one connection. We can date them, so we can date rocks quite accurately now, and we know that they have all of these same dates. We know that they have very similar chemical signatures, and it links all of these things together. And then the subsequent kind of mountain building. So yeah, that is I hope the 2-minute answer.
Thank you.
You're very welcome.
Any other questions for Dr. Guice? We're definitely going to have you back over, and Martin can invite you down to see their collections, which would be awesome. And we'd love to continue this relationship, and especially since you'll be at Johns Hopkins.
Yeah, absolutely. Yeah, thanks. Like I say, thanks for the invite, and I'll look forward to stopping by when I'm when things get a bit more normal and I'm at Hopkins. Yeah, for sure.
All right, thank you everybody for coming, and we'll hopefully see you at a program in person. Remember, next week it's Mustelids of Maryland, or Mustelids of North America, with our curator of mammals, Steve Sheffield, who's always fun to learn from. Everybody stay safe, stay curious, and maybe you've changed your mind about your favorite rock. We'll have to see if sedimentary would still win, but keep being curious, everybody. Take care.
Thank you, everybody.
Thank you, sir.